My name is Reagh Jacob. This is my partner Alex McNeil, and our project is developments in software-defined radios. Our external supervisor is Dr. Chen, and our internal supervisor is Dr. Elo. Now, despite the name of the project, it's actually a hardware project. It works with MIMO antenna systems, which are multiple input, multiple output systems, which are designed to support, or designed to exploit a signal propagation property called multipath, which basically states that if you have one transmit point and one receive point, the signal can and will propagate to that point by a number of different paths. And what MIMO systems attempt to do is exploit that by transmitting multiple signals over the same bandwidth and demultiplexing them based on what path they take to the receiver, which is called spatial multiplexing.
Okay, I'm just going to talk a little bit about space-time codes and how they relate to this project. Basically, space-time codes are a method employed to improve either the reliability or the throughput of a transmitted data stream in a wireless environment. So basically, space-time codes can only be used for systems that have more than one transmit antenna. So if we have a system that has like one transmit antenna and one receive antenna, we can't use space-time codes. Basically, space-time codes rely on transmitting multiple streams of data and recombining these at the receiver. So the two types of space-time codes that we're going to use for this project are the Alamuti code and the V-blast code. So the Alamuti code was actually developed in 1998, so it's a recent development. The requirements for this code are that we have a 2 transmit antenna, 1 receive antenna system. So if we have more than 1 receive antenna, this type of code will not work. The advantages are that the fading effects of the wireless channel are greatly reduced. That is, the bit error rate after coding is actually decreased. The disadvantages for this code are that we have a coding rate of 1, which means that in 2 symbol periods, we can only actually transmit 2 of the original symbols. So there's no overall advantage in throughput that's achieved. However, because of this type of coding, the decrease in bit error rate can actually be complemented if we use a higher order constellation scheme to gain improvements in the throughput. All space-time codes can actually be represented by this matrix notation that you see here, by matrix X, where the time is represented by the columns and the actual channel is represented by the rows. So we can see for the Alamuti code, at time 1, we're just transmitting symbol 1 and symbol 2 from antennas 1 and 2 respectively. And then at time 2, we're transmitting the negative complex conjugate of symbol 2 from antenna 1, followed by the complex conjugate of symbol 1 from antenna 2. Now, it sounds incredibly complicated, but what we're actually doing is over 2 symbol periods, we're actually transmitting symbol 1, symbol 2, or some variant of symbol 1 and symbol 2. And it's important to note that the receiver will receive all copies of the transmitted symbols, and then will rearrange these symbols in an optimal way such that we can reduce the overall fading of the channel. The second type of code that we're using is called V-blast, which stands for Vertical Bell Labs Layered Space-Time Code. And this type of code is nice because we have a coding rate of 2, which means that in 1 symbol period we can actually transmit 2 symbols, so we can increase our overall throughput. This type of code is also easy to implement. We don't have to take the complex conjugate of our original symbols. A disadvantage for this code is that it does not offer spatial diversity, which means that we can't actually combat the effects of fading for this type of code. Again, I have the same sort of matrix notation here. It's important to point out too, for this type of code, we have to have the same number of transmit antennas as receive antennas, or this type of code will not work. At time 1, we're just simply transmitting symbols 1 and 2 from antennas 1 and 2 respectively. And then at time 2, we're transmitting symbols 3 and 4 from antennas 1 and 2 respectively. So that means over 2 symbol periods, we're transmitting a total of 4 symbols, which means we have a coding rate of 2, so we've increased our throughput. So I'm going to talk now about the type of channel that we're going to use for this project. When I talk about the channel, I'm actually referring to the free space environment that exists between the transmitter and the receiver. So the 2 types of channels that were selected for this project are the relay channel and the Reagh channel. And these 2 types of channels were picked because they're actually most representative of the wireless LAN free space environment. The relay channel is actually considered to be the worst case scenario for a wireless LAN environment. This is because there's virtually no line of sight path that exists between the transmitter and the receiver. And this would actually be quite typical for a heavily populated urban environment where we might have trees in the way. Transmitted signals take multiple paths to arrive at the receiver, and signals arriving at different times will actually reduce the overall amplitude of the transmitted signal, and this is known as channel fading. Fading can either be fast or slow, depending upon the amount of activity that happens between the receiver and the transmitter. The second type of channel is the Reagh channel. This is similar to the relay channel in its fading effects. The primary difference between the Reagh channel is that there is a line of sight path between the transmitter and the receiver, so it's actually easier to detect signals that have passed through the Reagh channel. So I'll now pass it over to Greg, who will talk about the scope of the project.